Concrete. It's the most used building material on Earth. It was the building block of the Roman Empire. Today, it's the material for a new generation of gravity-defying skyscrapers. The raw ingredients that create this magic formula can be found in nearly every country on Earth. Yet how these simple components are mixed together can make the difference between tragedy and triumph. From the mundane to the massive. From the ordinary to the extraordinary. Concrete helped pave the way for innovation and laid the foundation for the world's greatest civilizations. Now, go inside the science of concrete. It starts out like liquid. When it dries, it becomes stone hard. This amazing metamorphosis has earned concrete the nickname liquid rock. It has served as a cornerstone of engineering for centuries. And it's a highly prized tool of construction for a reason.
It's easy to take concrete for granted. People see it in sidewalks and roads all the time, every day. But in fact, it is the closest thing to a miraculous material in construction that we've ever had.
Concrete is everywhere. It has an almost unlimited engineering potential. It can take on nearly any shape and forms the backbone of a variety of the world's construction. Superhighways, massive bridges, man-made waterways, mega dams, the world's tallest skyscrapers. This miracle material begs the question, how does it do it all?
I worked on a lot of jobs, and basically they all have a different formula for their concrete. Now, I can't imagine, the world without concrete.
The basic formula for concrete is simple. Sand, crushed rock, called aggregate, water, and the heart of the concrete mix, cement.
Cement, it is the grey, powdery material that acts as a glue that sticks all of the concrete together. It covers and coats all of the gravel, the sand, and the rock as a way of gluing and binding the whole material together.
To make cement, you need limestone, clay, and other elements like iron. These ingredients are crushed and combined into a powder that's poured into a kiln. The massive cylindrical spinning kilns heat the mixture to a temperature as high as 2,700 degrees Fahrenheit. The mixture becomes partially molten, forming a new marble-sized component called clinker. Once cooled, machines grind clinker into a superfine powder we know as cement. Cement binds the ingredients together. When added to sand, water, and crushed rock, the cement reacts, linking the raw elements into one powerful whole. Water is the key. When cement reacts to the water, it undergoes a transformation called hydration. During this reaction, a node forms on the surface of each cement particle. The node grows and expands, linking up with other nodes. It sticks to the crushed rock and sand in the mix. Cement binds these ingredients. As it solidifies, concrete becomes a building block of modern construction. This basic process hasn't changed in over a century. But creating concrete is no simple matter. Making the right recipe requires precision and flawless preparation. It is a synergy of ingredients and timing.
In a way, making concrete is like making a cake. There are lots of different recipes to make a cake. You get different flavors, different colors, different textures, but there are also lots of ways that you can make a cake wrong. It's not going to set properly, or it can come out in a way that's very different from your intentions.
Getting the recipe right is everything, and the consequences of a flawed mix can be deadly. The residents of Mexico City learned this the hard way. On September 19th, 1985, the Mexican capital is rocked by an 8.1 magnitude earthquake. It causes up to $5 billion in damages. Investigation of the rubble reveals that many of the buildings had been made of a substandard concrete.
Yes, we saw examples after the Mexican earthquake where when you use inferior concrete and you skimp on the rebar, and we saw both extensively in Mexico City, the concrete doesn't have its expected strength. The result is walls would fracture and shear and the building would collapse when the expectation would have been that the building should have easily survived to preserve health and safety.
The consequences of this quake are tragic. An estimated 10,000 die. Another 50,000 are injured. But with the right formula, structures made of concrete can endure thousands of years. Although other civilizations, including the Egyptians, experiment with concrete, the Romans transform it from a supporting material to a main substance. In Rome, liquid rock fuels the dreams of an empire. The word concrete even originates in Rome. From the Latin concretus, it means grown together or compounded. Roman concrete contains the traditional ingredients of sand, water, and crushed rock. But volcanic ash from the hills of Pozzuoli, Italy, transforms the material.
The Romans were very astute architects and engineers, and they recognized that by mixing volcanic ash from Lake Pozzuoli in Italy, they were able to get a concrete that became very hard.
This volcanic ash proves to be an adhesive binding agent. It gives ancient Rome a powerfully strong concrete. This innovation allows the Romans to craft an empire from the ground up. Concrete becomes the backbone of a dizzying array of structures, aqueducts, bathhouses, and markets. But today, one structure alone stands as a unique testament to the power of ancient Roman concrete: the Pantheon.
The Pantheon is one of the great architectural works of ancient Rome, with the wonderful colonnade that introduces the building, and then a huge drum covered by this amazing 142-foot dome, and that dome is made of concrete.
Constructed around 125 AD, the Pantheon has stood prominently in the center of Rome for over 1,800 years. It is one of the world's oldest buildings in continuous use. This former temple to the Roman gods combines elements of engineering and design, and nowhere is that more apparent than in this concrete dome. Stretching 142 feet in diameter, it is the largest surviving dome from the ancient world. It was the largest dome in Western Europe until the 15th century. Unlike modern-day domes, which are generally reinforced, the only material holding the dome of the Pantheon together is Roman concrete.
Constructing an unreinforced concrete dome on the scale of the Pantheon is just an incredible engineering achievement. You couldn't do something today because everybody would have praised the odds of your success as so small as you would never get a chance to do it.
The dome of the Pantheon is a stunning example of how Roman concrete could be built to last. Each layer of the dome becomes less dense the closer it gets to the top. At its weakest point, the Romans designed an oculus which reduced weight and stress. These innovations continue to impress engineers almost 2,000 years later.
For 1,500 years, that was the largest dome ever built by man. There aren't many engineered structures that stand that kind of record of time. And then all the countless use the Romans made for engineering aqueducts and other structures, roads, that made their civilization come together. So it's very difficult to imagine the Romans without concrete technology.
The Pantheon's one-two punch of engineering know-how and architectural innovation influenced many structures to come. Thomas Jefferson's Rotunda at the University of Virginia, the Low Library at Columbia University, but none comes close to the Pantheon's lasting power. With the fall of the Roman Empire, concrete is relegated to a supporting role. It is no longer the building material of choice. All that remains is the engineering brilliance of the Pantheon and other Roman structures made of concrete. Nearly 2,000 years later, builders would ask an almost impossible question. How do you conquer the land mass between two oceans? It holds more than 52 million gallons of water. It cuts a path straight through the heart of a nation. It is safely navigated by more than 12,000 ships every year. The Panama Canal. It's not one of the world's great rivers. It's an entirely man-made waterway. And the material that controls this much water is liquid rock, concrete.
By the late 19th century, the idea of a canal connecting across the isthmus somewhere in Central America had been floated for some time.
Before its construction, a trip by boat from New York to San Francisco meant sailing 13,600 miles and crossing through the deadly waters of Cape Horn.
The importance of the Panama Canal cannot be underestimated because before it existed, oil shipping had to take place between the Atlantic and the Pacific Ocean by going around Cape Horn, which is very treacherous, very severe storms for many months of the year, and many ships have been lost.
The massive storms along the Horn had been sending skilled sailors and precious cargo to the depths of the ocean. The world needs a better route, a safer route. February 1st, 1881. Ferdinand de Lesseps, the architect who crafted the Suez Canal in Egypt, decides to build another waterway through the country of Panama. Standing in his way are 51 miles of dense tropical jungle, torturous heat, and the fortress-like walls of Panama's central mountain range.
How do you cut through the Continental Divide? Unfortunately, they hadn't talked to the rock. If the devil could have designed a material to plague poor de Lesseps, he would have made this material. As soon as you expose it to air, it oxidized. You'd excavate, and it would slide in. It ended up to be just an impossible project.
De Lesseps' Panama Canal project quickly meets with disastrous consequences. 22,000 workers die due to landslides, tropical disease, and dynamite. After 8 years, the French abandon the canal project. But the French failure is not simply due to disease and the mounting death toll. From an engineering standpoint, their plan is flawed. With the American economy booming, an ambitious young nation takes over the canal project. President Teddy Roosevelt decides that U.S. workers are up to the task. American engineers learn from the French mistakes. The French tried to carve out a sea-level route through the difficult terrain, just like the Suez Canal. Instead, Americans use a series of chambers known as locks.
Locks are simply big concrete tubs that you put between two bodies of water that have different elevation. You put a concrete tub between them, and the tub has got to be higher than the highest water. And then you put doors on each end of the tub, watertight doors.
These chambers with doors fill with water, allowing ships to rise in steps. The ship crosses an artificial lake, then descends along a series of locks to the other side.
It's just a concrete tub with doors on each end that raises things from low water to high water, or the reverse works just fine. You open the high water end, sail in the ship, close the doors, turn on the pipes down here, the ship settles down to the low level, open those doors, and off you go.
With enough concrete, they hope to dam the Chagres River. By redirecting the river, they will feed the artificial lake and fill the locks. And the best option for the locks is liquid rock.
Without concrete, the Panama Canal would have been almost inconceivable. Certainly canals had been built before that. It's something that could be done, but at the scale that we were talking about, especially with the goals that they had in terms of timing, it would have been very, very difficult to do that without concrete.
The concrete locks will be a stairway bringing ships to the level of the lake. But they will need a high-strength concrete that can hold 26.7 million gallons of water for each lock. That's the equivalent of over 40 Olympic-sized swimming pools. Construction begins in 1904.
About 4.5 million cubic yards of concrete were used in the construction of the Panama Canal. And because so much concrete was needed, they had to set 8 on-site batch plants in order to produce that much concrete.
Other materials, like steel or aluminum, can rust or corrode in water. The advantage of concrete is that water can make it stronger.
Concrete needs water to complete its chemical reaction. If there's a little extra water around while it's going through the reaction, it just makes sure that all the concrete goes to completion in terms of its hydration. That's the chemical bonding caused by the water between the cement and the aggregate and the sand.
In order to prevent leaks, the concrete mix for the locks has to be very dense, not allowing any water to seep through.
The concrete that you need to build a canal is not the kind of concrete that you need if you want to design a skyscraper.
The recipe for the locks will try to be leak-proof. To solve this problem, builders choose smaller rocks for the aggregate in the mix. Tests show that adding finer aggregate creates a less porous concrete. The goal is a leak-proof lock that only expels water when the doors open. With the mix just right, engineers begin building the locks that will control the waterway between two oceans. At the Gatun locks on the Atlantic side, each lock chamber is big enough to hold 3 Statues of Liberty, laid end to end, with room to spare. At these locks alone, workers pour more than 1.53 million cubic meters of concrete. These locks link to the artificial lake made by damming the Chagres River, Gatun Lake. 9 years of construction. In May 1913, the last bucket of concrete is poured at the Gatun locks. Engineers prepare for the canal's first trial run. The tugboat Gatun travels through the locks on September 26th of that year. The locks work flawlessly and open for business 1 year later. Few engineering endeavors have changed the geography of the planet like the Panama Canal. After nearly a century in action, the concrete of the Panama Canal has stood the test of time. No other material has withstood wear and tear in the same way. Concrete linked 2 oceans, but an even bigger challenge awaits. How will concrete tame one of America's wildest rivers? Now go back inside the science of concrete. It has been called an American pyramid. The mighty Hoover Dam is a testament to the power of concrete. Weighing 6,600,000 tons, this concrete colossus holds back 45,000 pounds of water per square foot. The force of this water generates hydroelectric power for over 1 million people. From the neon lights of Las Vegas to the freeways of Los Angeles, this hydroelectric dam generates 2,080 megawatts of electricity. The Hoover Dam's construction redefined what the world could do with concrete, but it also rerouted one of America's greatest rivers, flooding ancient canyons, reshaping the area's natural habitat. In 1905, the Colorado River breaks free of a man-made canal. It floods Lower California across 150 square miles. Epic floods wipe out thousands of farmers. Millions of dollars are lost. The Colorado is unpredictable. The Southwest also has another problem: power. The boom towns of Los Angeles and Phoenix are growing at a rapid rate and desperately need energy. Raging floods and lack of power. Two different problems. But engineers believe there is one answer to both: dam the Colorado River. A hydroelectric plant would harness the natural power of the Colorado and, using simple mechanics, convert that energy into much needed electricity.
You're generally looking in the construction of a dam for a huge, solid structure. It's really about holding back enormous quantities of water.
The dam needs a material that is strong enough to hold back the raging Colorado. And since the location would be remote, able to be made on site, one material can meet all of those requirements.
It's hard to imagine the Hoover Dam being built out of any material other than concrete.
Using steel on this scale would be too costly. But to make the Hoover Dam, engineers would need more concrete than had ever been used before in one project. The dam will be 726 feet high and 1,244 feet wide. With a structure this big, it will be impossible to do one massive pour of concrete.
The amount of material that went into this dam was so enormous that there's no way to pour the concrete in one segment. So what they did is they divided the whole dam into lifts and then into individual blocks.
The Hoover Dam needs to be built as a series of individual blocks that will interconnect. Trapezoidal in shape, the blocks rise in 5-foot lifts. This crucial engineering element allows the project to progress in stages.
Something on that scale being built in concrete had not been built before. Hundreds of pounds per square inch, thousands of pounds per square foot on the base of the dam, trying to push the dam downriver. And now you've got the Hoover Dam to stand this incredible water pressure trying to push it down the river.
Chief Engineer Frank Crowe knows the completed dam will have to hold back 45,000 pounds per square foot of water. For this, they need a special high-strength formula. Crowe's solution? A minor but crucial modification to the standard concrete formula. A very dry mix, one that uses less water.
More water makes it more workable, but shrinks more, and shrinkage causes cracks. The less water, down to 7%, the better and stronger the concrete.
The dam's remote location also means crews will have to build 2 concrete mixing plants on site. Shipping a very dry concrete formula from a facility far away would render it useless by the time it's transported to the dam. Because speed is of the essence when working with a very dry concrete mix, the crews working the pouring cranes have to push themselves to the limit to pour quickly and accurately. When concrete cures, it gives off a powerful heat, a result of the cement and water reacting to make the rock-hard substance.
The process by which concrete cures, we call an exothermic reaction. By that I mean it gives off heat. And indeed, if someone pours a sidewalk or driveway around you, right after the slab dries enough to touch, put your hand on it. It'll feel warm. That exothermic, it gives off heat you can feel, sensible heat. As the amount of concrete going through this chemical reaction gets bigger and bigger and bigger and bigger, the amount of heat that's given off gets bigger and bigger and bigger.
Engineers calculate that if the dam were built in one continuous pour, the concrete would get so hot that it would take 125 years for it to cool to normal temperatures. The extreme heat would also cause the concrete to crack and crumble away. Concrete dries from the outside in. If the concrete is not evenly cooled, it can crack, putting the stability of the whole structure at risk. Instead, Frank Crow and his team of engineers have an innovative solution. Each block is outfitted with coils of thin-walled steel pipe. When the concrete is first poured, water from the Colorado River circulates through these pipes. The idea is to initiate a cooling process, but one done in stages. Cooling the concrete too quickly will cause it to crack. After the concrete has received its initial cooling, chilled water from a refrigeration plant is circulated through the coils to finish the cooling process. As each block is cooled, the pipes are cut off, and they are filled with grout by pneumatic grout guns, pumping 300 pounds per square inch of filler. Once the individual blocks have cooled and set, there is one final challenge. In order to prevent the hairline fissures between the blocks from weakening the dam, the individual blocks are formed with vertical interlocking grooves. When the concrete has cooled, grout is forced into these joints, bonding the entire structure into a monolithic concrete giant. This method takes advantage of one of concrete's fundamental properties.
Concrete as a material is very strong in compression. To build a structure, to make sure that the concrete is all in compression, you bend the beam like this, so now the water pushes on a column. Well, what's the water trying to do? It's trying to push that through. Well, it's the Pantheon Dome again. Only this time it's the water trying to do it. It's trying to push the dome through the river gorge. What that does is put the whole structure in compression. Well, concrete loves compression.
The more it is forced together while setting, the stronger concrete becomes. As a result of this property, the Hoover Dam is arguably stronger today than it was on opening day, 70 years ago. The Hoover Dam is a testament to engineering know-how and a skillful use of concrete. The dam contains enough concrete to pave a strip 16 feet wide and 8 inches thick from San Francisco to New York. More than 5 million barrels of cement were used in the Hoover Dam, and a total of 21,000 men worked on its construction.
And it represented an enormous engineering achievement to build successfully. It took the lives over 100 men to build that dam.
Today, the concrete megadam is nothing new. But Hoover set the stage and showed the world that concrete could do the job and help generate much-needed power. It changed the course of one of America's wildest rivers. Now the question is, can concrete conquer the skies? In the scorching Persian Gulf, a growing structure cuts the horizon. Its expected height is a closely guarded secret, but experts around the world agree the Burj Dubai may be the world's tallest skyscraper.
It'll be the tallest building, for sure, the overall title holder for some time to come.
A construction project this massive needs 11 cranes and the world's fastest high-capacity construction elevators. The building rises at the breakneck pace of one floor every 4 days. And from the walls to the floors, to the columns to the stairs, much of this desert skyscraper is concrete. More than 160,000 cubic meters of it. At more than 2,000 feet, the Burj Dubai will be the crown jewel of the United Arab Emirates and is a shining example of a new generation of skyscrapers that seek to dominate the skies. It is a far cry from the humble beginnings of the concrete skyscraper, more than a century ago. At the beginning of the 20th century, the building material of choice was not concrete, but steel.
You can build a hell of a skyscraper with steel. In fact, the Empire State Building is so overbuilt, you could probably add another 30 stories to it under today's building codes, and it would still comply fine. So steel was a great material. You can build a great building from steel, but it's an expensive way to go.
And steel is not only costly, but represents a challenge for a new generation of skyscrapers that grow increasingly higher.
And if you're going to go tall, the building's got to be stiff. It is so much easier to make those thick, stiff walls from reinforced concrete than steel that it's a no-brainer. The Petronas towers in Malaysia are concrete, and this new one in Dubai is going to be concrete. If you're going to go that high, it's going to be concrete.
The stiffness of concrete, combined with its availability and relatively low cost, have made it the building material of choice for these new skyscrapers.
As our experience and comfort level with reinforced concrete came along, and as the buildings started getting taller, reinforced concrete really became the material of choice.
Before 1902, the tallest steel reinforced concrete building is a paltry 6 stories tall. The Ingalls building in Cincinnati changes that. Engineer Henry Hooper dreams of a monolithic building of concrete, a skyscraper 16 stories tall. But many engineers believe that a concrete tower 16 stories high will collapse under strong winds or even its own weight. When Hooper finishes his building, there are many skeptics.
There's one anecdote that says that a reporter actually stayed up all night waiting for the Ingalls building to collapse because he was so certain that it was going to. Needless to say, the reporter was disappointed in the end.
It is a towering success for its time. But at 180 feet, it is just one in a dizzying array of modern-day skyscrapers. More than a century later, the towering dream of Dubai aims to be over 10 times the size of the Ingalls building. Every morning, workers assemble in the garage of the building. Erecting this much concrete in the punishing heat of the Gulf requires serious manpower. But before workers can pour a drop, the perfect formula needs to be mixed at the batch plant. The first problem this leviathan from the desert faces is its own height. The taller a building, the more it flexes, increasing the likelihood that it could flex to the breaking point, a deadly proposition. Older skyscrapers like the Empire State are safe because they use massive steel beams and braces. But erecting a tower nearly twice as high requires a material with even greater shock-absorbing qualities.
If you take something like the Empire State Building and the wind blows on the Empire State Building, well, the wind creates pressure, which are going to try and bend the Empire State Building over. But as you go higher, imagine now going twice the height of the Empire State Building. The wind gets more surface to work on. Indeed, buildings collapse when the flex is so great that the weight of the building gets outside of its footprint and the building doesn't have strength enough to handle that. Down it comes.
Builders will need a formula that is almost as strong as cast iron, yet more resistant to damage due to vibrations from the wind. After extensive computer and wind tunnel testing, the architects behind the Burj Dubai will use a high-strength concrete formula. It contains slag, a byproduct of the steel industry, and microsilica, which gives the concrete added strength.
If you look at the microstructure of concrete, there are many, many spaces between the particles that are either hollow, so we call them pores, or they are filled with water. Microsilica plays the role of filling these pore spaces between, and therefore it makes concrete much more dense, more durable, and stronger.
And in order to make sure that the formula is consistent, Alam Feroz, quality control manager for the concrete of the Burj Dubai, routinely tests the concrete before it is used in the skyscraper.
I'll give you an example. It's like if you're giving a blood to a patient, so how important is the blood to be tested before you give to the patient? It's a big risk. So same is with the concrete. When it has been tested, I get confident that whatever I am giving to the structure is being tested and it complies to the requirements. It won't be just a mere guess.
To test the strength of the concrete, small cubes are hardened in cool water. Next, the concrete is deposited into a crusher for a stress test. This cube holds up to nearly 14,000 pounds per square inch, making it a high-strength concrete. The concrete test has been successful. But as strong as this formula is, it still has to contend with desert heat. Temperatures top 120 degrees. How do you keep concrete cool in the desert? Builders use a deceptively simple technique. Shaved ice. While it's being mixed at the batch plant, slices of ice are mixed into the concrete so that it remains cool inside of the mix trucks. When it arrives at the building site, the melted ice has kept the concrete from overheating. But now, the concrete has to travel hundreds of feet into the air.
The key technical problem for building a building of this size and of this height is going to be to vertically pump concrete of the order of 2,000 feet high. It takes huge amounts of pressure.
Mixer trucks deliver the mix to the pumps. The building requires 3 pumping stations where the liquid concrete is poured. The high-pressure pumps force the concrete through a complex system of pipes.
Now, the technology to do so is awesome. If you think in terms of water, you have 1,000 feet of hydraulic water pressure. That's a tremendous kind of pressure. Now, concrete weighs 2.5 times as much as water. So you need a piping system that's so much stronger, and also pumps that are so much more efficient to pump concrete up that high.
As the sun sets, the second shift workers return to feed this growing skyscraper. The concrete pour takes place at night so that the concrete can harden evenly.
At the moment, even though it's 10 o'clock at night, it's about 100 degrees Fahrenheit, and the humidity is about 90%. The advantage of pouring concrete in these conditions, because the humidity is so high, we don't have a problem with it drying out the top surface of the concrete, but we've got effectively another roughly 130 stories to go.
As the pour continues into the night, the Burj Dubai has reached a milestone. 25% of the building is done. When completed, this megastructure will stand over 2,000 feet tall, making it twice as high as the Empire State. It will be covered in a reflective glaze to protect it from the extreme heat and high winds of the Gulf. But the building's guts are solidly concrete. When it's finished in 2008, the Burj Dubai will be the tallest building in the world. Like the Ingalls, the Burj Dubai has set the standard for its day, showing once again that concrete can be used in a variety of ways for the world's tallest buildings. Now, reinforced concrete is establishing itself as a building material of choice for skyscrapers. Concrete has conquered the skies. Concrete's next quest, how to tackle the building challenges of the future. Concrete has been a key ingredient in the construction of our civilization. It has been a fundamental part of our architectural past and is now paving the road for our future. Scientists are developing new formulas for concrete and are looking for ways to make it stronger, more environmentally friendly, and capable of doing things we never thought possible. Back where it all started, at the heart of the Roman Empire, concrete has taken a new and exciting turn. Just a few miles from the Pantheon, the Jubilee Church, designed by architect Richard Meyer, uses a new form of concrete. The church was commissioned by the Archdiocese of Rome to commemorate 2,000 years of Christianity. For that, the building would need a material that was both ancient and modern, a material that would speak to the church's past and make a bold statement for the future. They would also need a material that would last the test of time. Concrete fits the bill.
This church is remarkable for several reasons. It has these three sail-like forms, loosely representing the Holy Trinity, but made in effect of giant concrete blocks.
The shells of the church, which stretch out and up in the same way as the Sydney Opera House, are made of 346 white, reinforced, precast concrete blocks.
Concrete, for all of its advantages, does tend to pick up discolorations from the atmosphere and so on. Meyer, though, wanting to keep his building white, managed to work with local firms in order to achieve this concrete mix that included these photocatalytic particles that will absorb and neutralize the acids in the air. And in effect, what you'll have is a pollution-eating building.
Ital Cementi came up with a revolutionary new formula for the concrete that will keep it as pristine in 50 years as it was on opening day. All concrete structures tend to stain and degrade from pollution. Over time, this has given concrete a bad reputation. But the unique formula for the Jubilee Church contains a secret weapon: photocatalytic particles.
Now, in effect, what these do, when activated by the light of the sun, they mix with the acids in the air and neutralize those acids, neutralize the discoloration that would come typically from atmospheric pollutants. So, in a way, you kind of have a self-cleaning building.
This test demonstrates the photocatalytic particles at work. The concrete neutralizes pollutants, allowing it to maintain its brightness and not degrade over time. It is a revolutionary new development that has the potential to transform the way we look at concrete forever. Concrete isn't just working harder, it's working smarter. New developments in concrete technology now allow for what used to be unthinkable: helping the environment by using an unusual aggregate: glass.
The innovation here has been in making sure that the glass doesn't get corroded by the lime in the cement mixture. One of the biggest issues with concrete is that the Portland cement tends to be quite corrosive, and this has been a big problem with things like recycled glass. It tends to corrode the glass falls out. This composition of cement was actually developed by Columbia University. It is a much less corrosive, more benign cement, allowing you to put the glass chips in. So you can actually now have concrete with glass chips that actually has a good surface effect.
We are generating millions of tons of garbage, solid waste, and in New York City, approximately 6% of all solid waste is glass. That's bottles like this, yeah? And these bottles generally find their way into landfills. And that costs taxpayers hundreds of millions of dollars just to get rid of these bottles.
Concrete's versatility allows it to bind with other materials, in this case, glass. The first step is to separate the bottles by color.
And then you crush them in a crusher. Now, crushed glass is not something like this. This is what we call broken glass, and that is something you want to handle very carefully. It has sharp edges, and that was also one of the problems we were facing, because skeptics asked, well, if you use glass in concrete, won't people cut their hands by handling the blocks or whatever? Answer is no, because when you crush the bottles in a high-impact crusher, it comes out in pieces like that, and it's just like sand. It does not have sharp edges.
Eventually, the broken glass is crushed into a fine powder.
So this is just like powder, like baby powder, the same kind of particle sizes. So if you put this finely ground glass powder into concrete, you can replace part of the cement by this glass.
These are actually 100% recycled glass pieces added into the concrete.
Initially, scientists thought that recycled glass would make for a bad aggregate. But Professor Meyer and his team have found a way.
Okay, so once you make concrete out of these glass particles and color coordinate that very well, then you can get something like this, and this is now already being commercially produced. That's the way how regular concrete would look. And this is here our glass concrete, polished to a high precision, high grade of polishing. And that is known as terrazzo concrete.
Using recycled glass as an aggregate is just one of the many ways that concrete continues to reinvent itself. It also may pave the future for a more environmentally friendly concrete. There are also other developments reshaping concrete for the future. For the last 100 years, architects and builders have sought a way to allow light into concrete buildings, homes, and offices in a more efficient manner. One of concrete's biggest drawbacks is that it creates dark buildings that do not effectively conduct light. Experts are working to change this.
Okay, this is a piece of light transmitting concrete. It seems like an odd concept, but what they've done here is to take standard concrete and add glass fibers. Okay, so what you're seeing here is the blue LED passing through the glass fibers that are embedded in the concrete.
Imagine concrete allowing light to pass right through it, or for someone to cast a shadow through a concrete block.
This same thing can happen with normal daylight as well. So the idea is that you can build a structure with this concrete and allow daylight to actually come through the structural element of the concrete.
Light transmitting concrete, or litricon, is a unique form of concrete that uses glass fibers to conduct light. It allows for massive structures to permit light to shine through. This technology has the potential to redefine what concrete looks like. Once considered cold and impersonal, these new forms of concrete are transforming the material. What started off as the most basic of building materials is now on the cutting edge of building and design. The future for concrete is virtually limitless. If concrete is anything, it is a material that continuously reinvents itself. Concrete continues to adapt to the emerging challenges of our world and is laying the foundation for our future. Partially molten, forming a new marble-sized component called clinker. Once cooled, machines grind clinker into a superfine powder we know as cement. Cement binds the ingredients together. When added to sand, water, and crushed rock, the cement reacts, linking the raw elements into one powerful whole. Water is the key. When cement reacts to the water, it undergoes a transformation called hydration. During this reaction, a node forms on the surface of each cement particle. The node grows and expands, linking up with other nodes. It sticks to the crushed rock and sand in the mix. Cement binds these ingredients. As it solidifies, concrete becomes a building block of modern construction. This basic process hasn't changed in over a century. But creating concrete is no simple matter. Making the right recipe requires precision and flawless preparation. It is a synergy of ingredients and timing.
In a way, making concrete is like making a cake. There are lots of different recipes to make a cake. You get different flavors, different colors, different textures, but there are also lots of ways that you can make a cake wrong. It's not going to set properly, or it can come out in a way that's very different from your intentions.
Engineering potential. It can take on nearly any shape and forms the backbone of a variety of the world's construction. Superhighways, massive bridges, man-made waterways, mega dams, the world's tallest skyscrapers. This miracle material begs the question, how does it do it all?
I worked on a lot of jobs, and basically they all have a different formula for their concrete. Now I can't imagine the world without concrete.
The basic formula for concrete is simple. Sand, crushed rock, called aggregate, water, and the heart of the concrete mix, cement.
Cement, it is the grey, powdery material that acts as a glue that sticks all of the concrete together. It covers and coats all of the gravel, the sand, and the rock as a way of gluing and binding the whole material together.
To make cement, you need limestone, clay, and other elements like iron. These ingredients are crushed and combined into a powder that's poured into a kiln. The massive cylindrical spinning kilns heat the mixture to a temperature as high as 2,700 degrees Fahrenheit. The mixture becomes part of concrete. It's the most used building material on Earth. It was the building block of the Roman Empire. Today, it's the material for a new generation of gravity-defying skyscrapers. The raw ingredients that create this magic formula can be found in nearly every country on Earth. Yet how these simple components are mixed together can make the difference between tragedy and triumph. From the mundane to the massive. From the ordinary to the extraordinary. Concrete helped pave the way for innovation and laid the foundation for the world's greatest civilizations. Now, go inside the science of concrete. It starts out like liquid. When it dries, it becomes stone hard. This amazing metamorphosis has earned concrete the nickname liquid rock. It has served as a cornerstone of engineering for centuries. And it's a highly prized tool of construction for a reason.
It's easy to take concrete for granted. People see it in sidewalks and roads all the time, every day. But in fact, it is the closest thing to a miraculous material in construction that we've ever had.
Concrete is everywhere. It has an almost unlimited. The word concrete even originates in Rome. From the Latin concretus, it means grown together or compounded. Roman concrete contains the traditional ingredients of sand, water, and crushed rock. But volcanic ash from the hills of Pozzuoli, Italy, transforms the material.
The Romans were very astute architects and engineers, and they recognized that by mixing volcanic ash from Lake Pozzuoli in Italy, they were able to get a concrete that became very hard.
This volcanic ash proves to be an adhesive binding agent. It gives ancient Rome a powerfully strong concrete. This innovation allows the Romans to craft an empire from the ground up. Concrete becomes the backbone of a dizzying array of structures, aqueducts, bathhouses, and markets. But today, one structure alone stands as a unique testament to the power of ancient Roman concrete: the Pantheon.
The Pantheon is one of the great architectural works of ancient Rome, with a wonderful colonnade that introduces the building, and then a huge drum covered by this amazing 142-foot dome, and that dome is made of concrete.
Constructed around 125 AD, the Pantheon has stood prominently in the center of Rome for over 1,800 years. It is one of getting the recipe right is everything, and the consequences of a flawed mix can be deadly. The residents of Mexico City learned this the hard way. On September 19th, 1985, the Mexican capital is rocked by an 8.1 magnitude earthquake. It causes up to $5 billion in damages. Investigation of the rubble reveals that many of the buildings had been made of a substandard concrete.
Yes, we saw examples after the Mexican earthquake where when you use inferior concrete and you skimp on the rebar, and we saw both extensively in Mexico City, the concrete doesn't have its expected strength. The result is walls would fracture and shear and the building would collapse when the expectation would have been that the building should have easily survived to preserve health and safety.
The consequences of this quake are tragic. An estimated 10,000 die. Another 50,000 are injured. But with the right formula, structures made of concrete can endure thousands of years. Although other civilizations, including the Egyptians, experiment with concrete, the Romans transform it from a supporting material to a main substance. In Rome, liquid rock fuels the dreams of an empire.